So we continue on 9.2, photoelectric effect. So the definition of photoelectric effect: the emission of electron from the surface of a material when light photon strikes its surface. Okay, so let's say we have a metal, and then a light photon strikes on it. Okay, so this metal is negative, so electron will be emitted with some speed v, and the electron will have its mass m, so it can have the kinetic energy half mv squared. The electron emitted here we called as photoelectron. So we can get a formula which is E energy equal to work function W naught plus kinetic energy maximum. This energy comes from the light. The work function comes from the metal itself. Different metal will have different work function. And the kinetic energy is from the photoelectron electron emitted. So the work function W naught is actually equal to HF naught. HF naught is actually a threshold frequency. So we can get Hc over lambda naught, where F naught is the threshold frequency and lambda naught is threshold wavelength. Okay, let's see if we strike a red light color to the metal and the blue light color to the metal. Red light frequency. The red light frequency is lower than blue light frequency. For red light, there will be no electron emitted. Although you increase the intensity, how much intensity you put in here, there is no electron emitted because red light is low in frequency compared to blue. For blue frequency, if we strike the blue color, there will be electron ejected. Okay, so if we increase the intensity of blue color, so that means the number of electron ejected will be higher. So if we increase the intensity, the number of electron ejected will be higher. This is because the blue frequency is higher than the red frequency. Okay. To understand better, we will see the simulation of this photoelectric effect. Before we go through this photoelectric effect simulation, you already know that photoelectric effect is the emission of electron when the light falls on the material. So the electron emitted known as the photoelectron. Okay, so we have these different parameters. For example, intensity, what happens if we increase or decrease the intensity. We also have the wavelength. If we increase the wavelength, that means we decrease the frequency. Target material, we have zinc, copper, platinum, calcium, sodium. Also, we have the voltage and also current. And then we can look at what happened to the graph of current versus battery voltage, current versus light intensity, and electron energy versus light frequency. Okay, so let's say we set the frequency, for example, at 408 nanometer. Okay, and then what will happen if we increase the intensity? So if we increase the intensity, the electron ejected is become higher. Okay. If we decrease the frequency to a certain level, for example, if you can see, if we increase the frequency, there is no electron ejected. So the minimum frequency required to emit an electron is actually we call as threshold frequency. At certain point of frequency, there is no electron emitted. That level we call as threshold frequency. So for example, if we increase the frequency, we increase the wavelength, that means the frequency is decreased. So for example, at 701 nanometer, the color is red. So if we increase the intensity, no matter whether you increase or decrease, there is no electron emitted. So a minimum frequency is required for the electron to come out. So we need to have a fixed frequency that is higher than threshold frequency, maybe here, to eject an electron. So the electron emitted here we call as photoelectron. So I repeat, first we need to have a certain frequency higher than threshold frequency. Then we can increase the intensity so that the electron emitted is increased. Okay, next we have voltage and current here. So I will increase the negative potential. Okay, negative potential of the plate in the right side here. So the metal in the right side also negative, so the electron will repel. So let's say I increase the negative voltage here, you see, so the electron will repel. If you can see, when I increase the negative voltage, we are actually reducing the current to 0. Okay, when the current is at 0, that means this negative voltage here we call as stopping potential. Okay, so what will happen if we change the target material? For example, let's say I change to copper. So if we increase the intensity, there is no electron emitted. So the frequency really need very high at UV light so that the electron can only be ejected. Let's see if platinum. So if platinum, if we decrease the frequency, the intensity will increase also. So it really need a very high frequency so that the electron will be ejected. At this left plate, the kinetic energy is maximum. So we get kinetic energy equal to HF minus work function. Actually, different target material has different work function. What is work function? Work function is the minimum energy to remove electron from surface of the material. So the equation is work function equal to HF naught. Okay, let's see the graph. The first graph. Okay, let's say we change into sodium. If we increase the voltage, there is no change in current. Okay, then current. Okay, if we increase the intensity, the current also increase. That means current and intensity is linearly increased. And the last one, what happened if we increase the frequency? So the electron energy will be higher. So electron energy and light frequency is linearly increased. So this is the photoelectric effect experiment setup. This is the circuit. Okay, so what is the process? So the light will shine on the metal. So this metal is a cathode and electrons are ejected from plate A to C to the target material there. So electron moving from plate A to plate C will produce a current. So current can be measured with an ammeter here. When the positive voltage across the cathode and anode is increased by adjusting the rheostat, more photoelectrons reach the anode. Thus, the photoelectric current will increase. So as the positive voltage becomes sufficiently large, the photoelectric current reach a maximum constant value called saturation current. If the positive voltage is gradually decreased, the photoelectric current also decrease. Even at zero voltage, there are still some photoelectrons with sufficient energy can reach the anode, and photoelectric current flows is I naught. Okay, when the voltage is made negative by reversing the power supply terminal, photoelectron acted on by a retarding force. So as the V increase negatively, the current I will decrease because fewer photoelectrons have energies to overcome the retarding force. Okay, at a particular negative value of Vs here, the current I becomes 0. This is the value of negative potential which just stop the photoelectrons. So the photoelectron will be stopped with maximum kinetic energy from reaching anode. So the Vs here we call as stopping potential. Okay, there are 3 critical steps in the experiment that enables the determination of stopping potential. The first one is the plate C is negative to retard the motion of photoelectron. Second one, we vary the potential V until no current in ammeter. That means the I is 0. So this will signals that photoelectrons have been stopped from reaching plate C. Now let's look at the variation of photoelectric current I with voltage V. The first case is different for the light of different intensities, but its frequency is fixed. So the current increase with intensity but reach a saturation level Im for large values of voltage. So at voltage equals to or more negative than negative Vs here, the current is 0. So this photoelectric current is directly proportional to the intensity of the light. The frequency is fixed. All photoelectrons emitted have same amount of maximum kinetic energy. Okay, same value of stopping potential of Vs show that the maximum kinetic energy of photoelectron is independent of the intensity. The second one, for the light of different frequencies but the intensity is fixed. So the current depends on the intensity. Since intensity is fixed, the saturated current remain unchanged. So as here, the maximum kinetic energy increases linearly with frequency of light. The second frequency is high. The third cases for the different target material cathode, but the intensity and frequency of lights are fixed. So the current depends on the intensity, same. Since the intensity is fixed, saturated current also remain unchanged. Now let's see the failure of classical wave theory to justify the photoelectric effect. Number 1. From the experimental observation, it says electrons are emitted spontaneously. But from classical wave theory, says that an electron must gather sufficient energy before emission. So there is a time lapse between irradiation and emission. The delay will increase if intensity is low. Next, the maximum kinetic energy of photoelectron does not depend on intensity of light. Even if the light has very low intensity but has high frequency, it could eject photoelectron. But the classical wave theory said the higher the intensity, the greater the energy imparted to the metal surface. The last one, the existence of threshold frequency of photons. The emission of photoelectrons only occur when frequency more than threshold frequency. Mean that frequency of incident lights must exceed the threshold frequency. But the classical wave theory said that emission of photoelectrons occur for all frequency of radiation. Energy of wave is independent of frequency. Now let's try solve this question.